To find the deflection of the beams, we are going to start with one of the very popular methods, which is known as the second order method for finding the deflection. So essentially, remember, what we are trying to find is the relationship between the deflection y and the x-axis, that is along the length of the beam that is there. So let's see that how do we start with the second order method and how that helps us in find the deflection of the beams. Now first, I'm going to throw at you several formulas which you hopefully have seen from your basic elementary calculus or differential calculus. So these formulas, and you should be familiar with this, and this is our premise where we start. These essentially gives you the relationship between your curvature, that is kappa, that is there, and this relationship that you see over here with respect to the double derivative of the deflection and the first derivative of the deflection that you have over here. So this relationship that you see and the whole derivation of this one based on the elastic curve. Now remember, the deflected shape of the beam is known as the elastic curve that you have. Now this relationship, the derivation of this relationship is given over here, and we are not going to go much into the details of that. You should remember this from your elementary calculus, or if you have forgotten, you can take a look at this derivation. But essentially what you get at the end is something like this over here, which gives you an exact expression between the curvature and the deflection y that is there. Now remember that we are, in our case, we are predominantly looking at structures. For example, when we are looking at axial deformations or shear deformations or bending deformations, any kind of deformation. Deflection is also a type of deformation which is happening across the entire length of the body. We are always looking at small deformations and small deflections that is this. Now if we take this expression, and this is reproduced over here, now if we take a look at this one over here, you see your theta, that is tan theta dy of dx. So for small angles, you have theta equals to dy dx over here. Now for very small angles of rotation, this dy dx guy is already very small, and here you're squaring that one over here, so that becomes very, very negligible that you see. So now if you make that assumption that for small angle of rotation, so if you're looking at small angles of rotation that you have over here, this guy goes for a toss. So your kappa essentially becomes equals to d square y by dx square. So now if you again tie the loose ends back together, what do we get? We had already seen that our expression for kappa equals to 1 over rho, which is over here, and also we had seen is equals to m of x divided by ei, right? This is from the previous discussion that we had. Now this is also d square y by dx square, right? So now you take a look at this expression, and remember, this expression is strictly valid for small deflections. If you're looking at large deflection problems, then you have to start with this elaborate equation that you see over here. So for small deflection, this holds true. Now if you take a look at this relation, what we have just established is a relationship between the deflection y, the double derivative of this y, deflection of the y, and the moment over here. And since you start with a second order deflection, second order derivative of the deflection, and then how do we get the deflection from here? We have to integrate it twice. So that's why this particular method is known as the second order method. So let's write about this relationship, that it gives us a relationship between the deflection y and the bending moment m. Now that we have this particular relationship that is there, let's go ahead, and as we said that we are going to take this relationship that is there, that ei d square y by dx square, where what I have essentially done, I have essentially pulled this ei and taken over to the right side and did a little bit of rearrangement. So what I get is this important relationship that is there, which you are going to use quite extensively to find the deflection of the beams. And as I said, since we start with the second order derivative of the deflection, this method is also known as the second order method for finding the deflection of the beam. Now if you start with this guy over here, and then if you integrate it once and if you integrate it twice, let's see what we get over here. So if we just for integrate it once, what we will get is integration. Now here C1 is the constant of integration, and also you must remember one thing, that here we are assuming that your beam is prismatic, that your eye doesn't change, right? So this assumes that the beam is prismatic. If the beam is not prismatic, then in that particular case your eye also has to be here, and this integral, has to be m of x divided by I of x. Also remember one thing, that this dy of dx that you see over here for small angles, so we have the tan theta equals to dy over dx, or in other words, where tan theta for small angles becomes equals to theta. So for small angles we can write that this expression, that dy of dx, is nothing but equals to the theta. So that gives you, this theta is nothing but the slope of the beam, so that gives you an expression for the slope. So let's make a point of that as well. So once we have this, which gives us an expression for the slope, if we integrate it one more time, remember theta is nothing but dy of dx. So if we integrate it one more time, we are going to get the expression for y, which is the deflection. So let's do that. So this one gives you the deflection. Now you see in this equation, you have two constants of integration. So C1 and C2 are the constants of integration. And how do we get the C1 and C2? Simple, you get it from the boundary condition. So for a beam given a set of loading, you have to sort of go ahead and figure out that if you are doing the second order method, that what are the boundary conditions which I am going to use to determine this constant C1 and C2. So C1 and C2 are determined from the boundary condition. So we have determined C1 and C2 from the boundary conditions, and what can be some of the boundary conditions that you can think of. For example, for say if you are looking at simple statically determinate beam, so we'll start with some very simple examples. So you see here in this beam, for getting the two constants of integration, so a couple of boundary conditions for you can be that at x equals to 0. So for this beam, you see it's an overhang beam with a tip load at the end. At x equals to 0, you have y equals to 0. At x equals to this length, that is at b, you have y equals to 0. If you have a beam with a UDL at the left end, at the right end also, your deflections y equals to 0. Now for the cantilevers, this is a case where you have to make use of the y as well as the theta. We have an expression for the theta which depends only on your C1, right? And for this case, you see at the cantilever end, you have the deflection and as 0 as well as the slope as 0 as well. So these are some of the simple examples, but if you take a look at slightly more complicated examples with a variety of different kinds of loadings, so in that case you have to have some expressions for the continuity of the displacement and the slope. So let's go ahead and take a look at some of these examples to use the second order method to find the deflection of the beam and the slope of the beam. And let's see that how we use this method also for certain cases where you have an intermediate loading which requires you to establish further relationships of continuity between the displacements and the slope. So let's go ahead and do a couple of problems.